welcome to this virtual conference presentation. My name is Lars Albertsson. I run Scling, a data engineering startup based in Stockholm, Sweden. We provide data value extraction as a service, and in the very last slide, I will explain to you what that is. Today, we're going to talk about COVID-19 and data quality. We're going to look at a number of things that can go wrong regarding using data and data quality in the COVID-19 response and analytics. And we will see what we can learn from those mistakes and how we might solve a couple of the things with data engineering. I would like to emphasize that the goal of this presentation is not to argue or criticize for or against a particular response strategy. There are many people who have strong opinions out there. I am very aware that I am not qualified to have an informed opinion on pandemic response. I am, however, qualified to have an opinion on use of data. So let's look at one of the early uses of data for modeling the pandemic outcome. Early in the pandemic, there was a model from researchers at Imperial College who predicted with this model that the hundreds of thousands of people were going to die in Europe unless some drastic actions were taken. These outcomes influenced the UK to deviate from their planned pandemic runbook response to a more strict lockdown strategy, and many other countries followed. The conclusion from Imperial College was that since after the lockdown, hundreds of thousands of people didn't die, their model had saved many lives. Now, that sounds great. Unfortunately, it turned out not to be exactly true. And how do I know that? We can look at the countries that did not implement the lockdown strategy, for example, Sweden, and use Sweden as a tiny little control group for an experiment here. So this is graphs from some Swedish researchers who took the Imperial College model and made predictions for Sweden. On the left, you can see that the model predicted that hundreds of thousands of people will become hospitalized depending on the mitigation. The different colors and graphs are different mitigation strategies. And on the right, you can see that somewhere between 20,000 to 110,000 people would die, would be dead by July. Now, as we know, this didn't happen. What instead happens is this blue line. The orange line here is the Imperial College model without any mitigations. The gray line represents what the model predicted given what roughly corresponds to the strategy that Sweden chose. The blue line is what actually happened. And there's a huge difference here. Like the model is off by a factor of 25, which means that when the Imperial College researchers celebrated that they had saved lives, they actually celebrate the inaccuracy of their own model. How could this go so wrong? Well, I took a look at the source code. I would like to applaud them that they have released the source code. I think that is great. I hope we will see more of this and that it becomes mandatory for predictions like this. But unfortunately, the source code doesn't really look like source code. I don't know if you know C++, but I'm grown up with it, and it's not supposed to look like this. These screenshots are just parts of functions. The functions continue on forever and forever. There's no sign of decomposition or structure. It's just piles of lines of code. There are no tests that validate the function actually, or the model actually does something that it's intended to do. There are just a couple of regression tests which aren't actually used. And from a quick glance, it is apparent that this code can never with any confidence produce the right results. I'm not alone in this assessment of the model. This is from a code review by a Google engineer. And what's appalling here is the response from the Imperial College researchers who say, yes, there are some bugs, but we've fixed them now. But if you look in the history, you can see that there are some very critical bugs that have been previously in the model, and you can still find fairly critical bugs in the model just by simple code reviewing. Edinburgh University took this model and made some runs, and they found that if you change some parameters, purely technical parameters that are not supposed to affect the model outcome, like the number of threads, for example, the model differs by as much as 80,000 dead people, which after all is a lot. Doesn't matter. They're overestimating the number of dead. It does not just make us cautious. Well, no, unfortunately, there's no such thing as being cautious in pandemic response, because every action that you take has a great impact. Every action has a health cost as well. So, and I found this example from the Ebola pandemic to be very, very illustrative. That the graveness of the pandemic was so exaggerated in media and by model predictions like the ICL model, that people did not dare to go to hospitals. As a result, for every person that died in the Ebola pandemic, another 10 people died because from treatable illnesses because they didn't dare to go to hospital. So yes, so all models are wrong. Some models are useful, but some models are very harmful, such as these ones that exaggerate the fear. So how do you solve this? Well, you need to add software engineering expertise to the problem. This is a model that you use for a serious thing like this is a software project, and then in order to be responsive, you need to have software engineering expertise. And this is very much a solved problem. We know how to build high quality models. It's not rocket science. So there are other things that can go wrong apart from data processing. There are technical things that can go wrong in data collection and lack of quality assurance on models. And we can solve these things with data engineering, which we will look at later in the solution part. There are also non-technical things that can go wrong, things related to definitions and context and presentation and so forth. So let's look at a couple of those examples first. There are different definitions in place for what a COVID-19 fatality actually is. In Sweden, we use the first one here, that the infection is confirmed within the last 30 days before dying. There are also other variations, like confirmed sometime way back in the past, or some countries only count hospitalized fatalities, whereas the ones that die out of the hospitals are not counted, and so forth. And these differences make the numbers between countries difficult to compare. One number that is easy to compare is excess mortality, which is in a way is a high quality metric. And if you look at in the chart on the right, these are comparisons of the official metric of a country in comparison to the excess mortality. And we can see that some countries overcount COVID-19 fatalities a bit, but many countries undercount, and the differences are quite large. You also need context when interpreting data. This graph on the left was shown by the Swedish health authorities in late June, and in the graph you can clearly see a rise in the number of cases in Sweden, and this was interpreted by the World Health Organization as a new wave of a pandemic, so they were warning against these new outbreaks, which the Swedish health authorities said, no, you're just misinterpreting the data. Well, from the data that they showed, that's kind of the obvious conclusion. So what was missing here? What was missing was context. If you look at new cases, you also need to look at in this case, how many people are we testing? Because if you test more, of course, you get more cases. So in the lower right here, you see the number of tests executed at the same time, and then the lower left, you see measurements or new cases from different regions in Sweden, and the red bar here marks a increased testing effort. So you can see that the new cases are clearly related to the increased amount of test. You can also look at the same data, high quality data, but with different views, and then in the presentation you can get different conclusions. So these are graphs of both mortality in Sweden, and in the graph on the right, it seems that the pandemic is a major event, right, significantly affecting mortality. Whereas in the graph on the left, essentially the same numbers, it just looks like a little bump in an otherwise fairly flat graph. The difference here is the scale on the x-axis. It's smaller on the graph on the right, and also the scale on the y-axis starts at 0 in the graph on the left, but not on the graph on the right. So same numbers, same information, very different conclusions. And you can use this if you want to push an agenda. And this this graph is an example of a graph that has been floating in social media, where somebody is saying, oh, look, here's an obvious conclusion that happens to fit my agenda. And this graph has a number of problems. First of all, its y-axis is absolute numbers, which of course means that the large countries will float out on top because they have a large population. Also, the x-axis, on the x-axis 0 is the day when the case number 100 was detected within a country. And in a large country, that's very early in the pandemic phase. But in a smaller country, that is later. So the countries are shifted in time here. And therefore, the graphs are therefore not comparable. So you can perhaps make things better by showing absolute numbers, but you can still not compare large and small countries because the numbers will be diluted in large countries, and a couple of small countries where you have outbreaks will stand out. And comparing countries, it turns out to be too large a granularity, because these outbreaks, they spread in sizes of regions, like sizes of big cities. This graph on the right is from Sweden at the peak of the pandemic. And as you can see, the outbreak is very heavy in Stockholm and neighboring regions, but not some. We didn't have as much outbreak in other regions of Sweden. And the total numbers of Sweden were pointed out at the time in comparison to the neighboring countries, and said, look, we have much higher numbers, so therefore the obvious conclusion would be that the Swedish policy was bad. But if that had been the only explanation, then we would have seen a similar bad outcome in the rest of Sweden as well. It turns out that Sweden, except for Stockholm and the affected regions, had similar numbers as in the Nordics. So I don't know if this Swedish policy is terrible or not. I only know that nothing is obvious in this pandemic. So you might think at this point that I'm trying to defend the Swedish strategy. So let's look at some of the mistakes that the Swedish health authorities have been making. The graph on the left, the green bars, have been shown on every press meeting they've had. And every time they say, well, these are week-by-week numbers of cases in the EU, and do disregard the last bar because that's not a complete week, so it's artificially lower than the other bars. Every week they say this. And the lesson to learn, of course, is that if you have bars in the graph that are not comparable, they have to visually stand out, as they do in the example on the right, which is also from the Swedish health authorities. And the mistake of comparing things that are not actually comparable is very common. If you look at this graph, these are fatalities in Sweden. If you look at the graph, what's the conclusion to draw here? Well, if you don't have any more context information, the obvious conclusion to me is that the pandemic is now over. It's clearly declining very rapidly. The problem is that these bars are actually not comparable. So because the data collection takes time. So each bar has had a different amount of days for the data to be collected. And therefore, the bars on the left are very complete because for those days, a long time has passed. But the bars on the right are still missing lots of data. So I've seen these mistakes happen over and over again, not just in COVID-19, but in all sorts of environments. Why are they so frequent? They are frequent in traditional database and data warehouse-based processing environments, because the data collection is typically done by taking all the events that come in, and you put them in the database, and then you make a query towards the database, and you say, let us look at the latest data. Of course, we want the latest data and all of the data we have. It turns out, no, you don't want the latest data. You want comparable data so that you can draw intelligent conclusions. So let us again look at fatalities in Sweden, and this time we're looking at what we have at different dates. So on April 6th here, the gray line, we see that the trend is clearly going down. But if we wait a few days, we can conclude that, okay, it wasn't actually going down at that time, but now it's going down. And then we can continue to always conclude that it's going down. And if you do this every day, you get the graph on the left here. And you can see that for every day, we can draw it looks like from the graphics that the trend is going down. In the state of Georgia, they've taken this one step further, the article on the right here, and they actually backdate the cases. So when they find a new case, they don't date it with the date of discovery, but they timestamp it back in time to where the patients first had discovered symptoms. And this, even if you have perfect data collection, this basically guarantees that your trend will be downward facing or have a downward direction, which may or may not be in your interest, depending on your political agenda. So what do we do about it? Well, we need to include information about the data collection. So in this graph, we have colored the different bars with the latency of data collection here. And we see that after about a week, we have most of the data, but a bulk of the data is a few days late. So when we want to draw conclusions here, we have to, in order to get comparable data, we have to decide on the patients. So we could decide, for example, that we have a patients of 2 days, and then only look at the data that has arrived after a delay of 2 days, and that's the red line here. And you get low quality data because, as you see, there's lots of data missing, but we get comparable data. So we can look at if the trend is going up or down. If we want better data, we can wait for 6 days, and then we get the blue line here. But then we get higher quality data and can draw better conclusions. On the other hand, we have to wait for 6 days before we discard the last few days of data. So that's a drawback as well. If we want to try to have the best of both worlds, what we can do here is to do forecasting. We can add the data that we believe that we are missing based on historical trends. Unfortunately, this increases to the complexity. And it's not easy to do forecasting. You can select different models or algorithms, and you can select different parameters. How should we look a week back, 2 weeks back, 3 weeks back, a year back? Probably not for a pandemic, but that might be reasonable for sales, for example. The health authorities know how to do these things. They are analytically very competent. Why aren't they doing it? Why don't we see this graph shown on the press meetings? It's because although they know how to do it, it's too costly for them. So they could spend analytics time to do it, but they spend it on other things that they believe are more valuable. And why is it so costly? Or they are not alone here. They are doing this work in a fairly manual way. I don't have any knowledge from the inside, but I can see that from the statements that they're making, and in this case from the source code that they've also released. Thank you very much appreciated. So this source code, unlike the Imperial College mode, is respectable source code, and I have no complaints. But it's a manual tool. It's written by a manual craftsman or craftswoman. And you can deduce from the code and from the way they speak about their process that they're doing most of the work with manual analytics. Now, they are not alone here. Many companies work like this, but a few little share of the companies have actually figured out how to do this more efficiently on an industrial scale. Let me try to explain. For every value creation activity that we humans do, it starts out with a manual process. We have tools, but all of the energy is muscle powered, but from humans or horses or something. So whether it's forestry or transportation or cooking, it historically has started out as the humans doing everything. Then we have invented machines and electricity and motors to help us automate the things. We still do the same activities. Instead of horse and cart, we have a lorry and so forth. But it's much more efficient because we don't need to put in the human energy to make the things roll and make things go forward. But a human is still steering the process. It's not an automated thing. It's a human driving the lorry and so forth. If we want to go further from there, it doesn't help to get better tools. You cannot get a super lorry that will transport 10 times as much. Instead, you need to scale out the process and make it an industrial process. So and going from mechanized to industrialized, the challenges are no longer technical. The challenges are managing the scale and logistics and the organization and so forth, and dealing with faults. Because if you go to a industrial scale, faults will happen every day, and you need to deal with them. What does this mean for data? Well, the manual equivalent, or the muscle-powered equivalent of working with data, is working with tools like Excel or interactive BI tools, where you get raw data and you manually massage it to a refined piece of data artifact, the ones that we'll see in the graphs. We call these things a data set, a refined piece of more value than the raw data. A very large portion of data processing and data refinement is done in this manner today. Then you can pull in mechanized tools that can do these things automatically, and some companies have like the bulk of their activities at this stage. You see, and the tools that you see are typically data warehouses, databases, and some of the big data tools like Spark and Flink and so forth. At this level, the production is automated. So there's a regular job that runs every hour or every day, doing the refinement of the data. The outcomes are the data sets or the machine learning models are produced on a regular basis. But it's still controlled by humans. If something goes wrong, a human has to go in and fix things and so forth. Now, a small fraction of companies have made it beyond this stage. And what they have done is they have gone from a craft where humans control the steps to a process where humans work on improving the process so that they build data factories. So, for example, for our fatalities analytics, we decided that we want more than just one refinement process. We want to have multiple time windows. So then at the industrial level, we would improve the process here to do multiple calculations next to each other. And then we care about the quality, and so we need to, if we want to improve the quality further, we want to assess the quality of the incoming data so that we see that if there are gaps and can notify. And we also would like to assess the quality of the outgoing data after our processing, and perhaps test the data processing itself. The process. If there are quality issues, we can add new jobs that repair the data in an automatic way, that remove the duplicates, fill in time, correct timestamps, and so forth. And these repaired higher quality data sets, they are often reusable between different pipelines, between different use cases. So you typically don't see these linear pipelines. You see a mesh of pipelines with interdependencies and so forth. Repairment can often be complex and require additional data sources. So, for example, if you have mobile phones and you want to get geolocation data, but the GPS says that you are in the middle of the Atlantic, you might deduce that, hey, that's probably not right. So instead, I will repair this data by taking the IP address and doing an IP geolookup and get a higher quality intermediate data set from there. So we said that we wanted to do forecasting in order to have better analytics quicker. So now we're taking in even more data from historical data to do our forecasting for our analytics use case. But we don't know exactly which algorithm or which parameters we use. So we use multiple ones, and then we can manually assess and say, okay, algorithm number A here seems to be the best one. And for now, but we don't know that it will be the best one in the future. So we can add, in order to further improve our quality, we can add an assessment data pipeline that looks at the forecasting and looks at the outcome and measures different forecasting algorithms, and then alert us and say, hey, A used to be good, but now B seems to be better, and so forth. And all of this extra processing is done just for the one particular pipeline use case. So in data mature companies that have reached in this industrial level, you see these entourage of data flows and data pipelines around the main pipeline. So instead of just producing one data set per day, they might produce tens or hundreds of data sets just to improve the quality and improve the reliability of that one data set in the middle that they show on the graph. And this turns out to be even more important if you go to machine learning, where you can get away with using manual machine learning if you have a lot of luck. But machine learning is, unlike analytics, is quite poorly understood by humans. So it's even more important to assess the quality of incoming data, the quality of the model and its outcomes and so forth, and run A/B tests on users to validate which models are the best or how you should combine different models and so forth. So all in all, if you look at a few companies that have managed to raise themselves to this industrial data processing level, you see that the tooling that they have brought in is not so much actual processing tooling, but tools in terms of quality assessment and monitoring and validation and testing and continuous deployment, so forth. And also tools like workflow orchestration that ensures that the whole processes stick together and are resilient even in the case of faults, and that help you control the dependencies and so forth. And you almost never see this type of industrial processing outside of data platform, data lake environments. So the companies that have come to this level, all of the work that they put in is to improve the processes, not and very rarely to improve the actual data. And what this brings is to bring the cost down of data processing. If you're at an industrial level, the cost of doing yet another piece of processing is very, very low. So on the other hand, if you're at the manual stage, working with your Jupyter notebooks or your BI tools and so forth, the cost of refining a data set is high. So in an analyst team, you would see typically a few data sets generated per day because there's so much work going into each data set. The companies that have gone to the mechanized level, you usually have the data team that does all of the data processing, and they're using mechanized tools, and they are able to produce more data sets, perhaps up to 100. After that level, it tends to become too brittle. Whereas in the industrialized data companies, every team has the capability to deploy these pipelines and do calculations at an industrial level. And it's common to see each team having pipelines that generate hundreds or thousands of data sets. This graph here of pipelines and dependencies is from Spotify about 6 years ago, where they were producing 20,000 data sets per day. Nowadays, they are in the hundreds of thousands of data sets per day. Spotify is the most data industrialized company in Scandinavia. They are still behind Google, that produces on the order of a few billion data sets per day. That sounds great. Can I have this? No, I'm sorry, you can't. That is the quick answer. Because this is not a quick thing, and there are no systems or tools that you can buy out there. It doesn't help you don't automatically get there by going to the cloud or to Hadoop. And there are no consultants that can make you data industrialized, because this is not a change in technology. This is a change in processes, culture, and the way that you work and collaborate between the teams. And this knowledge and how to do that is limited to very few leading tech companies at this point in time, and a clique of startups. If you've been into in an agile transformation or DevOps transformation at a company, you'll recognize these patterns. It's not sufficient just to bring in some agile coaches or Kubernetes. That doesn't make you agile or DevOps. It's a journey that takes many years before you fully get there. You can get return on investment early, but you won't get maturity until much later. So these realizations is what made us start Scling. And why don't I see the these realizations was made us found Scling. We provide this industrial level data processing as an external service. So customers come to us with data, and we process the data. We host, we run, build the pipelines, we host the data and do all of the orchestration for them. We are humble in the sense that we know that we need customers' domain expertise, and so we collaborate closely with them. And we expect the customers to as well be humble and say, okay, but we trust you to know how to do data processing efficiently, and they need to trust us to use our tech stack and so forth. And in that model, we strive to create, to bring companies outside the little clique of most technical companies to this level of data industrialization. And we have cracked the code of how to do that without requiring the huge investments that that Spotify's and Google's of the world have put down into their data platforms. Thank you for listening, and stay safe out there. Wash your hands. Keep your distance. In particular, keep distance from the elderly who need more protection than the rest of us. Thank you very much.